Hey everybody, we have actually covered quite a bit so far in this unit. So we've talked about how to solve a quadratic equation in three different methods, right? We've used factoring, we have solved it by completing the square when it's not factorable, and we've also learned how to use the quadratic formula. So those actually give us some important points on the graph, as you'll see here in the next couple of days. But for right now, we're going to transition from the equations themselves into the quadratic functions and how to graph those. All right. So what I want you to do right now is graph this function here. Okay, this is the parent function of a quadratic. So I want you to see what shape it makes and pay attention to the table values and see if you notice anything that happens. All right. So to get you started off, what I want you to do is start off with we'll say -3, and I want you to plug in these different values to see what happens. All right, so pause this here and graph this. All right, so if we're substituting these input values into the x of the equation, all right, so we're actually just squaring everything, right? That's what the function's telling us to do. So -3 squared would be -3 times -3, so 9. -2 squared would be 4. -1 squared would be 1. 0 squared obviously is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. And what I was hoping you would notice is that we have a mirroring of values, right? We start to see some repeats in the range, right? The outputs. So we have some mirroring. And then, of course, we have the center point of 0, 0, right? So if we were to graph this, we would start at 0, 0, and then graph all of our other values. So 1, 1, 2 would be 4, 3 would be 9. Now, if you stopped here, you might think to yourself, well, this looks a lot like exponential growth, right? But because of the mirroring effect, we actually don't have a shrinking from left to right. We actually start to see it go back up on those mirror values. Right? So we have everything on the left side has a mirrored point on the right side. All right, so if we were connecting these, we want to make sure we connect them with a smooth curve, as smooth as possible anyway, with our freehand here. It's not a V, okay, so don't make that a sharp change at the bottom, right? It's not a sharp two vertical lines. These are actually curving ever so slightly upwards. So we should make that as smooth as possible. All right, so let's talk about graphing quadratic functions. Now you're going to want to take your time on these notes. There's a lot of terminology, a lot of things we're going to cover. So you guys should be treating the exit tickets as kind of a precursor to the test or the quiz on terminology. Okay, so it's important to know these names of parts, okay, of the graph. So let's take a look at what some of these main characteristics are. All right, so the one we just did was y equals x squared. We actually did f of x because we were using function notation, but it means the same thing, right? You can see that we have the 0, 0 point, the 1, 1, -1, and the 2, 4, and the -2, 4, and then of course the 3, 9, and the -3, 9. And this goes on forever, so we have the arrows on the ends. So this shape, every quadratic makes this shape. It is called a parabola. Okay, it's shaped like a bowl, right? It could be upside down if we had some reflection going on. So if this was pointing the opposite direction, it's still a parabola, even though it doesn't look like a bowl. It's just an upside down bowl. But it does always make this shape. Okay, something to note, it's never going to point to the left or right. It's either going to be up like this one, with the arrows going up, or it's going to point downwards. So parabola. Next thing we need to know is the vertex. Okay, the vertex by definition is either the highest point or the lowest point on the graph. All right, so in this case, our vertex is that 0, 0 point. All right, now if the graph is pointing upwards like this one, since it's the lowest point, it's called the minimum. all right? And if the graph was pointing the other direction, let's say it went downwards like this, then your vertex would be called the maximum, all right? So I'm going to be asking you questions, is the vertex a minimum or maximum? So it's important to know the difference. You can abbreviate that with min or max, that is fine. You don't have to spell the whole word out. And the last thing I want to talk about is the axis of symmetry. So the axis of symmetry, so we can get a color that stands out here, is the imaginary line. Okay, it's a vertical line that goes through the vertex. So in this particular graph, it's this imaginary line that passes through that vertex. And so everything on the left side is mirrored across to the right side. Picture the graph being folded over. Okay, that axis of symmetry would be the line in your paper that you would see if you unfolded it. All right, and we write this as an equation. Since it's a vertical line, it would be an x equals equation. So this particular one would be x equals 0. That would be the line of symmetry, or the axis of symmetry. All right, so let's talk about how would we go about graphing these if we had a little more to work with rather than just the parent function, and we had something in standard form. So we've got that ax squared plus bx plus c. Remember, that is standard form, so y or f of x is on one side and everything else is on the right side. So we can actually determine, without having to make a table, where that line of symmetry, that axis of symmetry, is located, and we can use this expression of x equals negative b over 2a, okay, using the b value here and the a value here, and that would actually tell us where that line of symmetry is. And if we look back here, let me go back a second, this x equals 0 makes sense if you think about the axis of symmetry actually tells you what the x value of the vertex is, right? This vertex was located at 0, 0. So it does give us this x value. So for this standard form equation, you can think of it as half of the distance between the two x-intercepts. So that's why it's negative 1b over 2a. It's negative 1/2 of the b over a. So once we have that axis of symmetry location, okay, that x value, we can find the rest of the vertex by substituting that number in for the x's in the equation and then solving for the y, just like we normally did with the linear functions, right? When we wanted to find one of our points, we plugged in the x value, we got the y value. We can also find, let me erase some of these stray marks here, we can also find the y-intercept pretty easily. And if you guys remember anything from x and y-intercepts, hopefully this got ingrained in your brain, all of our y-intercepts have an x value of 0, right? So if we substituted a 0 in for our x's here, well, that would make this term go away and this term go away. So our y-intercept is going to be whatever this constant value is. Okay, so that's actually another easy point to find and graph. Now, the nice thing about having a y-intercept is we can then reflect it across the other side of the line of symmetry in order to get another point without having to do a bunch of plug and chug. All right, so what I want you to do, and you're going to have to hand type this link in, is go to the graphing calculator on Desmos, all right? And this is going to give you an ax squared plus bx plus c equation, and you can kind of slide those a, b, and c parameters from left to right, positive and negative, and I want you to pay attention as you kind of fiddle with it a little bit, all right? I want you to look at where is the axis of symmetry, and more importantly, where's the vertex, okay? Which value, a, b, or c, seems to make this a minimum or maximum? So what makes the graph point up, and what makes the graph point down? You should also pay attention to the y-intercept, okay, as we just said on that previous slide, as you change the c value, or it's determined by the c value. So as you change c from positive to negative, you should see that y-intercept go up and down in correspondence with that. You might also notice the x-intercepts, and we'll talk about that more later. That has to do with why we solved the equations in the first place on 7.1 through 7.3. but do you notice how they move and which parameter, A, B, or C, which makes those change the most? Okay, and then finally what I want you to do is pay attention to what is the domain and range as you change things. Can you make any generalized universal statements about either the domain and range? All right, so pause this here, play with it a little bit, pay attention to these questions, see if you can kind of notate some changes that you notice. All right, so I'm going to go to Desmos here, and hopefully this is what you did. So as you move this A value, okay, so notice what happens if I go smaller, right? As my decimal gets smaller, this gets wider, right? So it's going to be compressed. What happens if I go to 0? Why did that go to a straight line when A is 0? Well, hopefully you notice that when A is 0, this turns into a linear equation. It just turns into bx plus c. So that's why A always has to be something other than 0 for it to be a quadratic. Then if you notice, as it goes down, as it goes negative, that made the graph or the parabola flip pointing downwards. So hopefully you notice that the A value tells you whether it's a minimum or maximum. If it's a positive number, it's a minimum, right? If it goes negative, then it's a maximum. And hopefully you also notice as we get bigger than 1, right, the bigger the number, the skinnier this parabola gets. This is a stretch. Okay, so let's go ahead and put this back to 1, if I can. Come on, let's refresh it here. Oh, shoot. Oh, let's go back to the thing here. Sorry about that. Oh, I can undo it. I should have just undone. Okay, so A is back to 1. So let's change B. And you'll notice B slides this kind of around the origin. We'll talk about this more later, but this is basically changing. Notice that the shape of the graph's not changing. It's just changing the left and right orientation. Okay, so we're talking about this more later, but this is basically what happens when you start introducing left and right shift. Okay, so then when we look at C, I didn't quite get this to 1. Oh well, just leave it alone. So as we move C, if I go negative, notice the whole graph shifts downwards, and as I go positive, it shifts upwards. Right? So that changes that y-intercept value. So even if you mess with these a bunch, as you slide this up and down, that y-intercept location is changing in correspondence. Okay, so let's talk about what this means. First of all, did you notice the domain is always the same? It's always negative infinity to positive infinity. Okay, so the domain remains the same. The range is determined by that vertex location. So it's either going to go from wherever the vertex is up to infinity, or it's going to start at negative infinity and stop at the vertex. All right, so let's talk about the steps, how you should approach graphing these, okay, with all this information. All right, so first thing you should do is if I give you a function, a quadratic function, you should calculate the axis of symmetry. Now remember, we're going to use that negative b over 2 times a value. Okay, that's going to give us the x for the next step, which is to figure out the vertex. Plug in the x from the axis of symmetry, determine the y, and then figure out if it's a minimum or maximum. Once you've determined that, you should be able to easily find the y-intercept because it's whatever that c value is. And then, of course, we can use symmetry to reflect that point over to the other side of the line. You just count how far away it is. And then finally, we're going to connect the points with a smooth curve, as smooth as possible, no sharp lines. All right, so let's look at this one as our example. All right, so f of x equals x squared plus 4x plus 3. So notice that our a value is a 1, our b value is a 4, and our c value is a 3. So the axis of symmetry is going to be negative 4 divided by 2 times 1, because that's my a and b values. So negative 4 divided by 2 is negative 2. So my vertex x value is going to be -2. I can also show that my equation for this axis of symmetry is x equals -2. All right, so then the second part is to substitute -2 in for our x's and simplify. So we're going to have a -2, don't forget to use parentheses so you don't mess up the signs, plus 4 times -2 plus 3. This is going to give me my y value of that vertex. So -2 squared is 4. 4 times -2 is -8. So 4 minus 8 is -4. -4 plus 3 is -1. So I have my first point, which is my vertex. So -2, -1. I also know my axis of symmetry. I'm drawing a dashed line because it's just imaginary. It's not really a line. My axis of symmetry does go through that point. Now, x-intercepts are also important. Oh, I'm sorry, I'm getting ahead of myself. So next we're going to figure out the y-intercept, which is easy because it's always going to be whatever the c value is. So this is located at 0, 3. So 0, 3 is here. And then we're going to reflect this point to the other side of the line. So we're going to count 1, 2 to the axis of symmetry, which means I have a reflected point 1, 2 over from the axis of symmetry to the left. Notice those are equidistant from that line, right? So then we're going to just connect this with as smooth a line as possible. We're just going to go up. So notice we're not making a table now. You could if you wanted to, but I want you to know how to do this just purely from the algebraic sense without having to do a bunch of substitution and plugging in. All right, our x-intercepts are here. We actually don't know where they are because we didn't solve for them, and we'll get to that later, okay? But could we use anything that we've learned in the past to find those points? That's the question I pose to you. The other thing I want to ask you is this vertex a minimum or a maximum? Well, hopefully you remembered that when this is positive, right, my a value is a 1, this is going to be a minimum because it's the lowest point on the graph. All right, so let's take a look at this one. If you want to pause this here and try to do it on your own, that'd be great. If you have an idea for the x-intercepts, now would be a great time to experiment. See if you can figure out what those are just based off what we've talked about and covered so far. Okay, so let's match up what you have with what I'm going to do here. We know my a is -2. My b is -8, and my c is -4. So if you want to do things in a different order, like, well, wow, I know the c is -4, so that's an easy one. It's going to be 0, -4. Okay, you can easily do that. Now, the other thing I want to look at is my axis of symmetry. So let's go ahead and do -b over 2 times a. So in this case, it's going to be a -8, watch your signs, divided by 2 times -2. Which is the same thing as 8 over -4. So -2 once again. So my axis of symmetry is x equals -2. I'm going to use that as my input to see what the y value is on the vertex. So I know my x is -2. Let's solve for the other piece. So we've got, I didn't leave myself a lot of space here. We've got y is going to be equal to -2 times that x of -2 squared minus 8 times -2. Remember, I'm just using the -2 as input, minus 4. So simplifying this, this is going to be -2 times 4 is -8, plus 16, which is 8. 8 minus 4 is 4. So my y value of that vertex is going to be, I forgot what it was already, 4. All right, so -2, 4. Let's go ahead and graph some of these points. I've got, let's see, -2, -4 is my vertex. I also know I have a y-intercept of 0. Oh, I went the wrong direction. Whoops. Mistake on my part. All right, so let's try that again. Negative 2 comma 4. I was wondering why I was running out of space. And then my y-intercept is 0, negative 4. Now I have my axis of symmetry here. So if you just count how many units this negative 4 is, it's 2 units. So I can just go 2 units this way and put another point. Okay, so let's go ahead and, well, let's not connect our graph yet. Let's see if you figured out how to figure out the y-intercepts. All right. Hopefully you remembered, this is my great hope for you, that x-intercepts all have a y of 0. So really what we're talking about is an equation where this is equal to 0. And this should look exactly like what we were doing in 7.1, 2, and 3, which is solving the equation. So that's the connection I need you to make. When you solve a quadratic equation, you're actually finding the zeros. You're actually finding the x-intercepts, also known as the roots. So let's see if we can simplify this, right? So let me see, I'm going to have to go here. It's negative 2x squared minus 8 minus 4. Negative 2x squared minus 8x minus 4 equals 0. So the first thing I should do, always, is look for a common factor. All these are divisible by negative 2, so I'm just going to factor that out. So now my 0 is equal to x squared plus 4x minus 2. Now, is this factorable? Do we have any factors of negative 2 that add up to 4? No, we don't. So we have two choices. We can either complete the square, or we can use the quadratic formula. I'm going to go ahead and just use the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c. All of it divided by 2 times a. Notice I used parentheses as I recommend. So our b value is 4. Our a value is 1. And our c value is negative 2. We're going to do the discriminant first, which is under the square root. So 4 squared is 16. Negative 4 times 1 is negative 4. Negative 4 times negative 2 is positive 8. So our discriminant is 24. So what I have after I simplify is negative 4 plus or minus the square root of 24 over 2. Now, 24 simplifies a little bit, so we can probably break this down a tad. It's 2 times 12. 2 times 6, and then of course 3 times 2. So this actually simplifies to negative 4 plus or minus 2 square root of 6 over 2. And if you want to take it one step further and simplify as much as possible, as you should, I know that 2 divides into 2 and negative 4. So I'm just going to reduce to negative 2 plus or minus the square root of 6. So that's a decimal. So when I go back to my problem, negative 2 plus or minus the square root of 6, those are actually my x-intercepts. I have 2 of them. I have negative 2 plus the square root of 6, comma 0. And I also have negative 2 minus the square root of 6, comma 0. Which seems confusing, but we're not going to find decimals right now. So really what I want to do is just graph this as smooth as possible. And then the only thing left to do is to identify what is my domain. The domain is always the same. It's going to be negative infinity to positive infinity. And my range is determined by this maximum here, right? This is a maximum. And it points downward. So it's actually going to start at negative infinity, and it's going to go all the way up to 4, and it includes it, so I put a bracket. All right, so you might need to watch that a couple times just to kind of see through the process, but let's just go back to the steps really fast as a point of reference. Just kind of go through this stepwise process, all right? We find the axis of symmetry, find your vertex, find your y-intercept, reflect it, find the x-intercepts if it asks for them, but otherwise that's all you really need to graph the function. All right, guys, see you in class.